Good evening, everybody. Good morning to Hari special. I don't know if there are other people from US or good afternoon to people in Europe. It's my real pleasure that Professor Hari Srikanth, whom we all know very, very well, he really does not need any formal introduction. It's just a matter of formality. I just have to tell a few words about him. Very friendly gentleman and a very kind physicist. I'm very glad and thankful to him that he has accepted my request to give this webinar. And it's very special today because this is the 25th webinar of this series of webinars on Spintronics. So we are kind of celebrating the silver jubilee in that way. And I'm glad that Hari is our guest today. So about Professor Hari Srikanth, he is now working as a distinguished university professor at University of South Florida in Tampa in US. So he has a strong Indian origin. He got his PhD in experimental condensed matter physics from Indian Institute of Science in Bangalore. After that, he pursued postdoctoral research at several places, and he joined the University of South Florida in 2000 and established the Functional Materials Laboratory, which has produced remarkable scientific output. His research spans a wide range of topics, including magnetization dynamics in nanostructures, applications of magnetic nanoparticles in nanomedicine and RF devices, magnetic refrigeration, spin caloritronics, spin injection, and so on. He has over 270 publications and has given over 200 invited talks around the world. In particularly last year, he was the IEEE Magnetic Society Distinguished Lecturer, and he really visited a lot of places to give talks and interacted with people. He's a fellow of the American Physical Society, a senior member of IEEE. He is currently serving as the editor for Journal of Alloys and Compounds, and also I think associate editor in Journal of Applied Physics. Hari has been closely involved with the MMM Interma conferences for more than 16 years as publication editor, publication chair, and program committees. He received the Fulbright Scholar Award from 2019 to 2022 to be visiting professor at Nanyang Technology in Singapore, and he is visiting many places. And I just would like to start with a small note or short note. When I was doing my PhD with Professor Wolfgang Kleemann, so I met Hari actually quite lately, I must admit. But during my PhD, during the period maybe 2005, around that period, so Professor Kleemann met Professor Hari Srikanth in some conference in US. And when he returned, of course, he had many things to tell, but first thing he told me that I met a very young, bright Indian physicist, very smart. He is, Professor Kleemann chooses his word very carefully. He told he's a very smart Indian guy, and you must meet him one day. And he's doing, because I was doing some work on magnetic nanoparticles, and Hari works a lot on those areas too. Professor Kleemann told me, and I became very glad when I met Hari, and finally 2 years ago, he visited NICER in this conference. So I'm really grateful to you, Hari, and I'm really looking forward to your talk, which seems very interesting to me, that kind of relating magnetic anisotropy to the spin Seebeck effect. So with this small short note, I request now Hari to start his lecture. And the participants, I request you to be patient. If you have any questions, please write in the chat window. After the lecture ends, we will take all the questions one by one. Thank you.
Thank you, Shubhankar. Good evening, Bhubaneswar, India, and also good morning to, I think, a couple of my students, my group members have logged in, hopefully. They wanted to attend this presentation. So it's a great honor and a pleasure to do this webinar, and especially since you mentioned that it is the 25th webinar. So I'm pretty much, it's an honor for me to give this talk today. Thank you for inviting me, Shubhankar, and all the organizers of this excellent Spintronics webinar series. I was in India 3 different times last year. So it is very strange for me that this year, not even once. So that's our life now. All of us are going through this ordeal. Hopefully in a few months, we should be able to move around, more freely, and things can revive again. But until that time, let's all be safe and stay healthy during this pandemic. So today I'm going to talk about the connection between magnetic anisotropy and Spin-Seebeck effect. I will, of course, start off with a fairly extended introduction because I know that there are many students and early career researchers that might have logged in. And I just wanted to make sure that you understand that everything goes back to Hall effect, different kinds of Hall effects, and Seebeck effect, of course, is related. And essentially, there are many different aspects that can give you a combined signature in some of these measurements. So I'll talk about Spin-Seebeck measurements and how one has to do it and how we do it, and share some of our results and the importance of the surface or the interface anisotropy in the magnetic materials that are generally used for generating spin currents. Okay. Again, this work, the Spin-Seebeck work, the spin caloritronics work that we did started a few years back, thanks to funding from the Army Research Office here that initially funded us. In fact, they helped us build the instrumentation for doing Spin-Seebeck measurements, which I'll discuss today. But our long-standing funding agency has been the U.S. DOE, which has been funded us for the past 12 years through extensions and grants. And I'm grateful for these agencies for enabling us our research and giving me an opportunity to discuss some of these things with you. Okay, first, I want to show you where Tampa is because some of you may not be familiar with where we are located. So here's a map of Florida. Florida is very similar to India because we are like a peninsula, water on 3 sides except the top. And Tampa is right there. It's on the west coast of Florida. It's on the Gulf Coast. This is the Gulf of Mexico. In fact, there are beautiful beaches here. This is not just me plugging my own city. There's a magazine that ranks all the top beaches in the country here. And Clearwater Beach. Clearwater is a suburb, beach suburb of Tampa, and the Clearwater Community Beach is considered ranked number one for many years running. So we are located in a very, ideal place as far as the location is concerned. A little bit about my university. I would like to welcome you to Tampa whenever you can travel next year or after that, and also to USF. A little bit about our university. We are a pretty large university, one of the biggest public universities in the country. We are number 12 in terms of size, close to 48,000 now, 48,000 students. With Tampa being the main campus, we have more than 30,000 students here. You don't see too many of them these days because of the Corona restrictions. Many of them are taking classes remotely, but generally this is a very nice, vibrant campus with a lot of students. Something unique about my department, I'm in the physics department here, and it turns out that we offer the only applied physics PhD in the state of Florida. Now, this is a big deal because there are other major universities in Florida that you might have heard of. University of Florida, which is the flagship university in Gainesville. Florida State University in Tallahassee, where the National Magnet Lab is. And those of you working in magnetism may know about that. Some of the huge pulsed field magnets, 60 Tesla and more, are located there. But none of these departments in other universities here offer a PhD in applied physics, so we are unique. So if you're looking to get a PhD in applied physics near the beach, we are the only choice. So please pass the word around. We would love to get some students from India and especially from Odisha. Okay, so I would also like to present basically some of my team members right here, current team members. This talk and all the talks that I give would not be possible because unless these guys work hard and basically they made these contributions. I work closely with a colleague, Professor Manhuang Fan. We often co-mentor most of our postdocs and students. And here are some of the current postdocs, and I've listed only the ones that are involved, that have been involved in the past and are involved right now in this work that I'm going to talk about. And here are some students. A lot of the early work that I'll present today has been done by Dr. Vijay. He was my former PhD student. He's now a postdoc at Colorado State University with Professor Mingjong Wu. Dr. Raja Das was a postdoc here for several years, and he's now a faculty member in Vietnam. These two initiated the efforts actually in this area. And more recently, we have a postdoc that has just arrived from India, Amit Chanda. Actually, Amit's advisor is logged in. I can see Professor Mahendran. So Amit got his PhD from NUS in Singapore. And we are lucky that after waiting for several months, we made the offer to him early in the year, and then he had to wait till travel as possible. And we are so happy to have him here with us right now. Balu is another postdoc in the joint group, and he's an expert in transport properties. So the couple of students that are working in this area are Terry. We call him Terry Changmin Hung. He's interested in right now doing spin transfer torque experiments at National Taiwan University, and he'll be here next early in the spring. And one of our new students, PhD students, is Noah Schultz, and he has just started off, and he's going to do some of the work that I'll talk about towards the end, the new work. We work on a number of areas, and some of you might be familiar with some of our work in these areas. Today's topic is going to be spin caloritronics and what I call spinterface physics. Okay, so this is something, it's a buzzword, spinterface. So I'm going to use that to identify exactly what we mean by these spinterfaces. We also work a lot on many other areas, and I'm not going to go into them. As in any magnetic measurements lab, experimental lab, we have a lot of experiments that we can do here. We have a PPMS, two of them actually, which one of them is always cold. The other one we fill in helium whenever we need to do experiments. We can do transport measurements, AC, DC magnetization. A couple of experiments that I'm going to talk about today is radio frequency transfer susceptibility. This is sort of a signature experiment that we do in my group. We introduced this experiment, which is based on a tunnel diode oscillator. It's a self-resonant circuit that is extremely sensitive for looking at very fine features in the magnetic properties, especially anisotropy. We can measure the effective anisotropy and the switching. The other experiment is the spin-Seebeck effect, of course. You may be familiar with this. There are several groups that are doing these experiments, and I'm going to discuss how we do this and put this in perspective with what other people are doing. We can also do a lot of other experiments, but I won't go into those in today's talk. All right, so the outline of my talk, I'll start off, as I said, with introduction to caloric effects, especially Hall effects. We'll start with basic Seebeck effect and then Hall effects and the different kinds of Hall effects. Then the main part of the talk is going to be discussing some of our recent observations, recent in the sense we've been doing this for the past 3 to 4 years now. So essentially, we'll talk about YIG. This is one of the materials that is standard in the community now in spin calorics. Everybody has to actually measure what's going on with YIG, yttrium ion garnet. And more recently, we also have some very high quality thulium ion garnet through some collaborations, and we're looking at some of these heterostructures. And the key word that you will see throughout my presentation today is anisotropy, and how magnetic anisotropy can play an extremely critical role in actually even giving you the figure of merit, which is longitudinal spin Seebeck effect, which I will define a little later. Again, one of the most important things we feel is to try to use buffer layers between the ferromagnet and the metal on top, and that can have a very strong influence on the transfer of spin current, and eventually this is known as the spin mixing conductance. Ways to improve spin mixing conductance is something that I will also discuss towards the later part of the talk. Okay, so let's start with a nice figure here, schematic. If you look at the left here, Spintronics in general can be divided into 4 quadrants, whether you're doing current control, field control, you control using light, and then magnetic field control, right? So essentially, you can see many of these well-known areas that are currently being researched around the world and also in India, including Bhubaneswar, in your group, in Subhankar's group and other groups in India. You can see the multiferroics is here, electric field control effects are seen there, optical effects. In fact, spin Hall effect was first very well demonstrated and spin injection in semiconductors using optical means. We know that many years back. What I'm going to talk about is essentially this part right here, which depends on using a magnetic field and also temperature and the spin Seebeck effect or the spin motive force. Now, if you switch to the right-hand side, you can see that it's always nice to have a triangle. The multiferroics community uses this a lot to look at coupling across the interface between different phases. So here, if you look at spin, charge, heat, you can define various fields. For example, Spintronics has to do with manipulating charge and spin transport and the coupling between them. Heat and charge is thermoelectric, very well known, established technology and science. Several advances have been made in more recent years in chalcogenides, for example. And this is what we will focus on today, spin caloritronics. In other words, how do we use heat to manipulate spin current? And also how do we establish the connection between temperature gradients and spin current? Of course, the reverse, this is the spin Seebeck. We can also look at the spin Peltier effect, which is the reverse effect. All right, so let's step back, and I want to use the next few slides for the benefit of students mainly to discuss some of the things that you already have learned in textbooks. Whatever textbook you open, like Ashcroft and Mermin or any solid state physics, textbook, you learn the fundamentals of these things. So I won't go into the details, of course. So you can all club these here on this slide as spin-independent non-equilibrium transport, okay? So that includes the Seebeck effect, the Thomson effect, the Peltier effect, very well known. The applications, clearly, a lot of applications, including sensors, cooling, and most importantly, try to harvest energy from waste heat. And this is an area that is really important for future when we need to when we have the energy crunch, we need to maybe be able to look at materials and devices that can help us with energy transfer. And of course, the most important effect, one of the most important effects, in my opinion, ever to emerge in terms of transport properties over the past 60 to 70 years is the Hall effect. And this is just a Wikipedia image right here, just shows you the Hall geometry. You've got essentially a magnetic field in that direction. You apply a voltage and in the longitudinal direction, and because of the well-known Lorentz force, the carriers, basically the trajectories of the carriers cause the charges to pile up on either side, which sets up the Hall voltage. This is something that we already know. So the reason I say Hall effect is because there are several types of Hall effects. I'll mention that, and they become important, especially when you start getting into new magnetic materials, including topological systems, for example, magnetic materials with skyrmions in them, for example. Nernst effect is exactly the same as Hall effect. Instead of applying a bias voltage here, you replace that by a temperature gradient, okay? So essentially it's the analog of Hall effect, but instead of the voltage, you apply a temperature gradient, and that drives the thermal current here, charges, and you measure the Hall voltage. So this is also called the Nernst-Ettinghausen effect, okay? The applications, again, are quite obvious. So if you go further, what happens is that once you have a magnetic material which has a magnetization, internal moment, then we talk about spin-dependent non-equilibrium phenomena. And the first thing, one of the most important discoveries, is the anomalous Hall effect, okay? The anomalous Hall effect basically has this extra term here where the Hall resistance is also going to be determined by the internal magnetization of the material. It's a ferromagnetic material. There are several contributions to this that can lead to understanding various kinds of anomalous Hall effects that have been observed. You can club them into two different categories. One of them is extrinsic. This is primarily because the spins, whether they're up or down of the electrons actually in this case are moving, right? They're carrying the spins. So basically, the up or down spins can be scattered in different ways, and there are different mechanisms, and I don't have time to go into the details. So these can cause this extra, anomalous Hall effect that is observed. And something that is really interesting is that there could also be an intrinsic phase winding. This is known as the Berry phase effect in momentum space. It is applicable in systems where you have built-in topological, interesting objects. This could be due to spin frustration, geometric frustration in materials where it's intrinsic. It could be due to some twist in the spins, some helical, order that is seen in some of these magnetic materials. And of course, these can also help us understand the so-called topological Hall effect, where it's primarily the Hall effect, especially the anomalous Hall effect that you see depends on the topology of the materials. And one of them is, of course, could be skyrmions. For example, skyrmion can be thought of as a very dense, twist in the spin, like a vortex, right, which is very stable. And that can cause, when a charge carrier, a spin passes close to it, you obviously get the effect that leads to a winding in the phase. So that's how we understand the Berry phase and all the related effects. Now, analogous to the, remember that all of these is related to spin orbit interaction, although the exact mechanisms could be different. So one really is not very clear about how the spin orbit interaction plays roles, an important role in many of these effects. In fact, spin orbit scattering and interaction is considered, again, I consider that as one of the most important things that still we need to understand. And that's why many of these experiments are going on. The anomalous Nernst effect is very similar, as the Nernst effect was similar to the Hall effect. Here, instead of the, applying a voltage, for example, you can actually have a temperature gradient. So that's, for example, how you can observe the anomalous Nernst effect. Keep in mind that in Nernst effect, we're usually talking about materials where there's a movement of charge carriers. Okay, so essentially the charge carriers which carry the spin, they result in the Nernst effect. Okay, so all of these are originating from spin orbit coupling in general. There are many papers that can demonstrate this very clearly. Let's continue further. Now we get into non-equilibrium phenomena, spin-dependent non-equilibrium phenomena, and we can define what is most important and relevant, these two effects for the observation of the spin Seebeck effect. Okay, and this is the spin Hall effect. The spin Hall effect, again, is an extremely important prediction by Diakonov and Perel back in the 1970s. And after that, in the 90s, it became really interesting, late 90s. In fact, the person that coined the term spin Hall effect is Jorge Hirsch. He's a professor at University of California, San Diego. And he, in fact, is the same person that is behind this so-called H index that most universities use these days to track the citation impact factor of publications of different people, right? So that's the same Hirsch index. Okay, so essentially spin Hall effect is analogous to the anomalous Hall effect, but here it doesn't require any broken time reversal symmetry. And again, the most important thing is it is due to spin orbit coupling. The mechanisms are pretty much the same as in the anomalous Nernst effect and Hall effect. The analog of the spin Hall effect is the inverse spin Hall effect, and this is because of the Onsager reciprocity relation. You can show that, you can explain this inverse spin Hall effect. And this is used because, when you have a spin current, pure spin current, right? That's your pure spin current, JS here. If you have a pure spin current spinning up the spin Hall voltage over here, well, measuring spin current is rather difficult, right? So one way to measure is to measure a voltage. So we have to convert it back to a charge current. And that's how we design the geometry of these structures when making spin Seebeck effect measurements. So this one actually converts the spin current to charge current through, again, spin orbit interaction. And that is what is used to detect the spin Seebeck effect. Now, I have one more slide of introduction before I go into the experimental details. We talk about spin currents, right? Now, keep in mind that there are different kinds of spin currents. So when we talk about pure spin currents, here's a simple schematic again describing various ways of looking at spin currents. For example, the basic mechanism, the basic ways, of course, goes back to the Stoner model, which essentially shows that there's an imbalance in the population density of upspins and downspins in ferromagnets at the density of states, which means it favors the transport of polarized transport of one type of spins. So that's one way of generating and manipulating spin currents, right? We can also think of spin current, a pure spin current, if, for example, charges move exactly in the opposite direction, so the charges cancel out, and you still have an effective spin current present in the system. But the most interesting spin current that we're interested in for the spin Seebeck measurements is magnon-based spin current. And this is important because here we don't talk about the charge moving. We talk about the propagation of the spin current through the coupled excitation of, which as magnons, right? Essentially coupled excitation of the magnetic lattice, which can carry energy and angular momentum. So it can actually propagate a spin current through this process in insulators. That's the most important thing, in magnetic insulators where the charges themselves don't move. And this has made life a lot easier to measure this, because if you have the charge moving and the spin it takes also with it. It's often very difficult to decouple the different effects that can result when you apply a thermal gradient. So working with insulators is the way to go. Ferromagnetic insulators is the way to go to make sure that what you're measuring is related to spin Seebeck rather than the other effects, such as the Nernst effect. Okay, so now we can come to spin caloritronics and how we do these experiments. Okay, again, spin caloritronics refers to non-equilibrium phenomena that can be related to spin, charge, entropy, and energy transferring materials in general. Specifically, how do we do these spin Seebeck effect measurements? Spin Seebeck effect has been observed. It got people excited for several years now because it was observed in ferromagnetic metals, insulators, semiconductors, you name it. Every material had something like a spin Seebeck effect. And part of that is because of the measurement geometry, and also because people are measuring different kinds of effects and calling it spin Seebeck, whereas strictly it is not. And that's why I went through all these definitions of different kinds of effects that come into play. All right. So what do we mean by spin Seebeck effect and how do we measure it? We want to make sure that we only drive a pure spin current, and the geometry that is used, the bottom here, is this is called the longitudinal configuration. I am not going to talk about this. In fact, not many people do this configuration anymore because it sort of mixes both the longitudinal and transverse, and people have abandoned this. So most of the people in the community doing the spin Seebeck studies use the longitudinal geometry. Okay, so at the bottom, the gray one here is your magnetic insulator, and that's the key word. It's an insulator, so we don't have the charges mobile. Okay, the carriers basically. So, and then you set up a temperature gradient in the perpendicular across the thickness here. You set up you magnetize the specimen. Ideally, you want a single domain material, right? So ideally, you magnetize it, you saturate it so that it's a single domain structure. Otherwise, it could complicate things if you've got domains in there. So you try to apply a sufficient field in that direction. And then on top, the blue thing here is a platinum strip. Okay, it's a metal strip, and you measure the voltage because of the charge buildup. I'll explain to you in a minute. And that is your longitudinal. That's how you get the longitudinal spin Seebeck effect. Okay, you measure the inverse spin Hall voltage. That's what you do. So think of this as the thermal gradient pumps the spins across the interface from a magnetic insulator like YIG, yttrium ion garnet, into a platinum. And the reason we choose platinum and some other few choices is because of its large spin orbit interaction. You need to have a metal that has a strong spin orbit coupling so that essentially the spin current is converted into a voltage by the inverse spin Hall effect process. And this voltage is sufficiently large for you to be able to measure and also use in devices. Okay, so that's basically why you need the metal is important here. And the most important thing that I will tell you today is the interface between the insulator and the metal, and one has to pay real close attention to that. All right, so there's a nice paper here by a group, a combination of groups here from from Italy, Japan, US, and all that, where they actually compare the different kinds of measurements. If you're interested, you should go and look at this group, look at this paper here, and there are also some related papers. So what do we mean by the spin Seebeck coefficient? This is our definition of the longitudinal spin Seebeck coefficient. It's actually the voltage that you measure divided by the length, that is the longitudinal length of the platinum there on top, divided by the temperature gradient, of course, and then divided by the thickness. Okay, so that gives you some kind of a figure of merit, and that's what we will be measuring and plotting against field and temperature. Okay, so this is how we do it in our lab, and that's a very recent picture. As you can see, Amit here that's our system. It's based on a cryogenic probe station. After Vijay left, it was not used for a while, and there's another student there. There's Noah there. Noah and Amit are working together here, and they're trying to revive this setup here so that we can actually do these measurements. So the nice thing about the system is that we can apply a magnetic field. It has an electromagnet. We can apply a field up to about half a Tesla, 0.6 Tesla. And it's a top loading system. So as you can see, get on top of this table, isolation table here, and you can actually mount the sample and, in whatever way you want. The heating is done by typically Peltier elements. We actually have the bottom that is countersunk to the base, which has a cold finger. so you can actually control the temperature, and the heating on the top is done with a Peltier element, or there are other ways of doing it. And also the temperature is measured by either resistive thermometers or Cernox, or the usual ways of measuring temperature sensor. Okay, so that's how we do it. We can apply a magnetic field. We can apply a thermal gradient. We can generate several kelvins in thermal gradient across the thickness of YIG, and then we measure the longitudinal spin Seebeck effect. So this is a custom design system that we took a couple of years for us to really develop and calibrate, but it's now working well, and we can measure really even very tiny signals in many samples. We have also reproduced this inside a PPMS, and of course that gives us the ability to apply large magnetic fields because of the superconducting magnet, and also do these experiments at a much larger range in temperature. The cryogenic probe station, right now we can go down to liquid nitrogen. If needed, we can go lower. It has a Janus cryogenic system there. But this is again a PPMS. It's pretty modular, as many of you know, and we've also developed a measurement that we can do inside the PPMS. Okay. All right. So let's look at, just one reason why I keep saying YIG is because this is one of the best magnetic insulators, which has a very low Gilbert damping. In fact, it has the lowest magnetic damping among all the magnetic materials known, right? And it has a very reasonably high Curie temperature, so we can make devices at room temperature. It's an insulator, and because of the low damping, you can have long magnon propagation length, and that is important because you need to generate magnons in the YIG and pump it across into the platinum, and that could be a fairly sizable distance. If it's a thin film, it could be several, it could be up to a micron. If it's a single crystal, even bigger. Okay, so that's why we need materials with long magnon propagation length, and YIG is a great candidate. Magnetite, ferrites are also excellent candidates for this. Okay, the YIG itself has its own very interesting physics, because if you look at the iron, it goes into the octahedral and tetrahedral sites, and depending on the vacancies, you can have very interesting built-in anisotropy in YIG, and we'll see that momentarily, why the anisotropy in YIG can give rise to very interesting aspects of the spin Seebeck effect. So I'm going to show you some of the data from other groups, and then I'll show you some of the data that we get, right? Our data pretty much mimics many of these data. So if you look at the data, this is from, I think, the Mainz group in Professor Matthias Claui's group in the University of Mainz in Germany. And then the Tohoku group, they were one of the pioneers in this field, having discovered this effect many years back. And also a group from Brazil. So all of these are plotted here. And you can see one of the things, if you look at this one, let's look at this one right here. This is the spin Seebeck effect in microvolt per Kelvin, very disappointing numbers, right? So that's one thing. We need to increase the figure of merit. We need to find ways to improve the spin Seebeck effect. If we need to compete with thermoelectric devices, which is very well established, we need to get this figure of merit up, okay? But as a magnetism community, we're excited because we know that spin control is much better than charge control in devices in general, and the power consumption is low, so we can actually make very robust, efficient, higher efficiency devices if you're able to generate the right kind of heterostructures and increase this effect. So that's one of the goals in this community, in this field. If you look at the spin Seebeck effect, this is the LSSE, the longitudinal spin Seebeck, as a function of temperature. Pretty much in YIG, most groups that see this quite routinely, you see a peak. You see a peak here, it increases and decreases. Sometimes the peak is smaller, depends on the thickness of the sample. Sometimes it is pretty much washed out, but it is there, okay? It is there at about 80 Kelvin or so. Now, students, if you open any textbook in solid state and look at a curve that looks like this, what does it remind you? Thermal conductivity, right? Thermal conductivity looks like that. And it's a thermal measurement. So there was initially a lot of people that were promoting models and theories that explain this due to phonon contribution, right? Magnon, phonons, and those kind of things. While phonon contribution could be there, it's now clear that this peak has nothing to do with the standard phonon freezing effect that gives rise to this this kind of a shape in thermal conductivity measurements. For example, the phonons in this system freeze at much lower temperatures, 20 Kelvin or so, okay? So this peak is anomalous because it's at a much higher temperature. So it cannot be just due to that phonon freezing. So now it is understood after a lot of models came out that this is dominated by a Magnon effect, okay? So essentially you can model this as an increase in the Magnon diffusion or relaxation length, right? As you lower the temperature, the Magnon propagation length increases. However, at very low temperatures, the density or the number of Magnons reduce. So it's a competing effect that gives you a field at a much higher temperature. So that's what comes out of this. So we call this the temperature anomaly that is seen in these thin Seebeck structures. Another anomaly is seen and first reported by the Tohoku group is this one right here. And what they see is that if you look at the same, sorry that this got cut off. This is the spin Seebeck effect as a function of magnetic field. It looks like a magnetization curve. However, there's a step here at low fields. So it looks like there's a step here and then it increases. Okay, it's almost as if there's some kind of two different magnetizations or two different magnetic orders that are present in there. So this step is visible, and we also see it in our measurements. And this has been ascribed to this unusual property of YIG, where the surface has a perpendicular magnetic anisotropy and it is different from the bulk. Okay, so again, that's what Tohoku group first ascribed it to, and we wanted to check that using different means. We wanted to also measure the anisotropy, and that's something. So this is the field anomaly, the fact that you see in the field dependence, you see some kind of a step at low fields. Okay, so now we wanted to investigate. Now I'm going to talk about results from our lab for the remaining time. And so the first thing that I would like to discuss is the effect of magnetic anisotropy. It's very clear that in YIG, in the YIG-based devices, magnetic anisotropy, especially the fact that you have bulk and surface anisotropy and how they influence the spin current, because the spin current has to go through all these layers to reach the platinum, right? So the influence of the effective magnetic anisotropy on this thing, we wanted to investigate this. Some of our early reports came out in this paper, and we have another more recent paper on this subject. So essentially, that's what we set out to do. This is our data. As you can see, this is the field dependence. We also see the field anomaly. Just to be consistent, we get values here, small values. This is in nanovolts. Okay, consistent with what the other people are seeing. But we also noted, and that we reported in this paper, is that there is a temperature dependence at high temperatures. There's another anomaly around 200 Kelvin. And this was missed by the other groups. It was there in their data, but they did not interpret it. So we actually think that this already has to do with the so-called single ion anisotropy, which leads to the spin reorientation at that temperature. And this has been noted before. And that is because, as I told you, the iron vacancies can order in the tetrahedral. They have a preferential orientation in the octahedral, with respect to the tetrahedral side. So that can give rise to an internal anisotropy, and that results in this tiny glitch. So essentially what I'm saying is that the spin Seebeck signal is mimicking any kind of magnetic anomalies or magnetic properties of the system. It is just mimicking it, okay? So if we believe that this is due to the magnetic anisotropy or the difference in anisotropy between the bulk and the surface, we should be able to see it in some other magnetic measurement. So what measurement we use for looking at the anisotropy, and this is something, as I said, a signature experiment that we do to measure the magnetic properties in many materials. We use a self-resonant technique based on a tunnel diode oscillator. What it does is basically this whole thing goes into a PPMS, so we can actually change the external DC field and temperature and measure the change in inductance of this coil, LC resonator, right? That's what it is. It is driven by a tunnel diode. So we can bias this tunnel diode in the in the negative resistance region. If you remember your tunnel diode characteristics, your IV, the I goes down at a certain region of bias voltage and then goes up. So if you bias it there, it acts as basically it supplies power to oscillate, right? So it acts as a power supply, and then that drives it into an oscillation. So we can make this a very precise self-resonant oscillator, ultra stable oscillator. So we use that with the sample in there. The transverse configuration is because the DC field, by the superconducting magnet, by the PPMS, for example, is perpendicular to the small RF field, and that sets up this transverse susceptibility measurement. So we can actually measure the change in susceptibility from looking at the change in the resonance frequency. The sensitivity is much higher than many other experiments that you can use to measure susceptibility, because we can detect few hertz change in an overall resonance of 25 megahertz. So we can do the math. We can get parts per million resolution. So any fine structure, any fine changes as a function of magnetic field or temperature will be picked up in a very sensitive manner with this experiment. And we were one of the first ones to introduce this, to look at a variety of magnetic materials. And also one can use this to study superconductors and penetration depths in that too. Now, why transverse? Why do this? Why can't we just do the conventional longitudinal susceptibility? This dates back to a theory paper by Amika Maharoni, who's well-known theorist in magnetism. In one of his papers, and what he did was he calculated analytically both the conventional susceptibility and the transverse susceptibility. And note that the transverse susceptibility is the projection of the magnetization in the transverse direction, so it's a tensor, okay? So this is from his paper, his old paper, 1957 paper. As you can see, this is like taking the derivative of your magnetization, right? So if you go, it's a unipolar scan from positive to negative, reduced field with respect to the anisotropy field. As you know, anisotropy field is one of the most important, characteristic energy scales for magnets. This is just uniaxial anisotropy. This was calculated for just a Stroner-Wolfrath single domain particle, okay, t equal to 0 calculation. So you can see that the parallel susceptibility, as you would expect, shows a singular peak when the polarity switches, like taking the derivative of your dm by dh of your MH curve. Now the transverse shows two symmetric peaks. In addition to this peak right here, it shows two symmetric peaks, and these are located at the anisotropy field. So that gives a very sensitive way of directly measuring the effective anisotropy field in different materials. And that's what we've been using to look at many, many different samples. That's our geometry. So we essentially verified or validated Aharoni's prediction in the 1950s that transverse susceptibility can be used for directly observing or measuring the effective anisotropy. Okay, so this is just to show you that, yeah, we see the peaks. We've been seeing peaks for 20 years now on different kinds of materials. This is one of our standard experiments we do to look at ferromagnetic materials and devices, for example. And we can actually read off the effective anisotropy field from this. We've been looking at nanoparticles. I'm not going to go through this. We can actually follow this in the HT plane across the super paramagnetic blocking transition and get the complete magnetization dynamics in one experiment. Okay, so that's the power of this experiment. And we now can remember this can be used for looking at the anisotropy in our LSSC devices, the heterostructures that we made with the YIG and platinum. That's the data I'm going to show you next. So yeah, so we did that. Now we know, since we know that we can measure magnetic anisotropy very precisely using a totally different experiment, let's use that on the same heterostructures and see if we indeed pick up these so-called two different anisotropies in YIG, namely the bulk and the surface or the interface, right, between platinum. I just want you to focus because I don't have much time, so I want to keep going so that I can give you as much exciting information. So you can see, remember that it should have only two peaks, right, at the anisotropy fields, but now you can see that there are two on each side. So essentially, we identify these HS and HK as the two different anisotropies, one related to the bulk of YIG and the other related to the surface. Excuse me, I'll take a sip of water. In fact, I believe our experiment here is one of the first evidence of actually decoupling or differentiating between two different types of anisotropies that exist, and that also explain the low field anomaly that we see in the LSSC signal. Okay, we plotted everything here together. As you can see, this is our anisotropy. This is HK that we get from transverse susceptibility on the right hand side. This axis is VLSSC, the spin Seebeck, and you can see that they all show this. Excuse me. I promise this is not a COVID cough. So this is just a scratchy throat. So you can see that they all show a similar kind of change. And so we can relate that whatever we are seeing in the spin Seebeck effect, LSSC, the longitudinal spin Seebeck effect, also shows up, or rather the other way around. Whatever you see in anisotropy, any kind of effect in the anisotropy temperature dependence also shows up in the spin Seebeck. So spin Seebeck effect is very sensitive to magnetic anisotropy or changes of the magnetic properties of the insulator, ferromagnetic insulator that you're using. We also can show that the low field, the second peak in the transverse susceptibility also shows a temperature dependence, and guess where the peak is? Exactly where the LSSE peak is, 80 Kelvin. So we can actually reproduce and make a direct correlation between the effective magnetic anisotropy measured by a completely different experiment, which very powerfully probes the effect of anisotropy with the LSSE. Okay, so that's one of the first demonstrations here of connecting them and saying, yeah, anisotropy does play a huge impact or influence on the spin Seebeck effect. Now the next step is, and this is pretty exciting, this is one of our more recent works. We published a paper this year in Materials Horizons, which has like an impact factor of 18 or 20 or something like that. Okay, so so what we wanted to do was, now that we know that the spin Seebeck effect is so sensitive to the anisotropy, what can we do? Can we change the anisotropy between the interface? In other words, think about it, take a step back. The perpendicular magnetic anisotropy, the surface or the interface of ig and platinum, is not good because it kind of breaks the symmetry. You want the pure spin current not being subject to any other kind of different types of anisotropy, right? Magnetization or ordering. So essentially, what we thought was, let's put some buffer layers. Now, this is not our original, idea, because there are other groups, especially Chia-Ling Chen's group and Johns Hopkins, have been investigating the use of copper. Copper has a fairly large spin relaxation length, spin diffusion length. And so essentially using copper, tungsten as a buffer layer between ig and platinum. But we wanted to try something different. We wanted to try an organic semiconductor, C60. And the reason for that, I'll mention to you in a minute. So I'm going to show you some of the results of how do we control or change the interface properties by perhaps changing the anisotropy, effective anisotropy, and see what influence or what effect it has on the spin Seebeck effect. I would like to ask Shubhankar, is it okay to take a few minutes extra past 9 o'clock my time, since we started late?
No problem. You can take another.
Okay.
No issues.
Yeah, I would probably take about another 15 to 20 minutes. Is that okay?
Yeah, it's fine.
Yeah, okay, thank you. Because this is a very important effect, and also I want to show you some of the more recent work that we're doing. Okay, so let's look at this, what we did. So here, the motivation, as I said, is that we need to improve the spin Seebeck effect in order to achieve efficient devices. Remember, we have to compete with thermoelectrics, right? And do better than them. So we need to go quite a distance in terms of doing that, improving the devices. There have been reports of buffer layers like copper, tungsten. Some of them shows high signal, some of them don't show. So it is very unclear what the buffer layer plays a role. And again, keep in mind that the efficient spin injection depends on the so-called spin mixing conductance at the interface. This is how the spins mix between, or the spin orbit interaction takes over effectively in the platinum when the spins are moving across the interface. So some kind of interface transparency is for spin transport is what is important. So this reminds me, or let me remind you that this goes back to the days of organic spintronics. Remember, there was a lot of excitement, right? And even now it's an exciting field to try to inject spins into organic systems, right? Very challenging because of the interface properties. So we are faced with a similar situation in this spin caloritronics community, that we have to really pay attention to the interface between the generator of spins and the top layer, the metallic layer. Okay, so our goal was to add a semiconductor, and a simple reason is as follows: because it's an insulator, it's a very good insulator, Ig, and then platinum is a good metal. Why don't we have, the conductivity mismatch is very high, right? So instead of having such an abrupt mismatch, can we add a semiconductor in between them? But the choice of the semiconductor has to be done very carefully, because you cannot, add any material, because the spin orbit scattering or coupling in them could again further kill the effect, kill the spins, right? It'll make it worse. So we have to choose a material where it is well known that the spin orbit coupling is extremely low, very low. And of course, organics are a great choice for that. That's why we chose organic semiconductors, so that basically we can try to not interfere with the spin transport or the spin propagation between YIG into the platinum, where we use the inverse spin Hall effect. So let us choose something where there's a very weak spin orbit, coupling, so that it doesn't interfere with it much. So that's basically what it is. It turns out also, if you look at this old work from University of Georgia, is basically C60 has a very large spin spin diffusion length. Okay, C70 is even better. So somebody can give us C70, we'll be happy to try that as a buffer layer. But these are extremely large, so that is good, because we are trying to guarantee here that the spin diffusion length being large means that we are giving the spins, the magnons, more chance to propagate, higher chance to propagate without getting scattered to the platinum, where we want to measure the highest possible signal that we want, the spin signal. Okay, so this is our device now. So we have the YIG and we have C60 layer in between. We can change the thickness. We've done a few thicknesses. I'll show you. Platinum on top, and we do the thing. The interface is extremely nice, very good. This is in collaboration with Professor Wynn at University of Georgia, who's an expert in growing organic C60 on top of different inorganic layers. So we work with single crystals. We also work with thin films. Okay, I'm just going to show you some of the early single crystal data. Single crystals we get from commercially from Crystal Systems in Japan. Okay, so let me quickly go through this data. So this is basically one of our, next slide will be one of the most important ones. So we measured the spin Seebeck with and without the C60, and I'm just going to show you the 5 nanometer thickness, because there seems to be a magic number here in terms of the appropriate thickness of C60 that enhances the spin Seebeck effect. All I want to pay attention is just these two, okay? This is basically without a 0 nanometer C60. In other words, no C60, just the YIG platinum. You see the value here, okay? You see the value here. This is the field dependence. You see the value here. Look at this right here. There is a jump of almost 800% in the spin Seebeck effect just with the introduction of 5 nanometers C60 organic semiconductor. There's the low temperature anomaly is still there, but it's much weaker, okay? So what we think, and I'll show you some other work also confirming this, what we think we're seeing here is that the presence of C60 actually benefits the overall effective anisotropy by removing the surface anisotropy on the YIG, the interface anisotropy. And that actually improves the chance of a larger spin current, and eventually leads to a larger observation of spin Seebeck. So this is promising, because if we can find an appropriate layer, we can actually start competing in terms of the signal, the figure of merit for the spin Seebeck effect. So the intermediate layer is very important, okay? By the way, we did the first spin Seebeck, which is generating thermal gradient. There's a group in Germany from Halle, Professor Schmidt's group, and they actually did a similar experiment with C60 deposited on YIG, but they did the FMR spin pumping experiment. Of course, you can do you can measure the inverse spin Hall effect either by thermal gradient or by FMR pumping. So they did the FMR pumping, and see this, they get the highest value at about a C60 thickness of 5 nanometers, which is exactly what we also observed. We also observed a similar trend. As you increase or decrease the thickness, we do see that the effect is reduced. Okay, so it is consistent with a completely different experiment, the FMR pumping experiment, spin pumping experiment. So we're quite happy to see that there's some kind of a corroboration here in terms of the effect itself. Again, just to go through this, we get a pretty large value, and this is the main thing here. At low temperature, of course, but still not that low. You can get about 800% increase in LSSC, and even at room temperature is much higher. That's again shows you how the trend goes at low temperature. It goes up, and especially the 5 nanometers, it just takes off. So this is again the spin Seebeck effect in microvolts. It turns out, if you look at this is an interesting correlation here. This is from Dr. Gwynn's prior work at the University of Utah, where you can actually measure that this is actually the spin diffusion length in C60 as a function of temperature, and there is a similarity. So clearly, this seems to track the spin diffusion length. So as long if you have a long spin diffusion length, which you get at low temperatures, it seems to benefit the increase in spin Seebeck. So it all makes sense. That's what I'm saying, that there are ways to improve the spin Seebeck effect, and it all seems to make sense perfectly when you use these buffer layers. So that opens up an opportunity to look at a variety of interesting aspects of different types of buffer layers. I'm going to skip this. I'm not going to go through the details. We can actually model it using a toy model. So this is basically looking at the spin mixing conductance, and now we can put in the C60 thickness and all that, and we can actually generate the increase in the spin Seebeck spin current and also the spin Seebeck coefficient, which is related to that. We can actually generate using a simple model like this. An interesting slide, important thing is that we did experiments of transfer susceptibility just on the YIG platinum, YIG C60 platinum. This is a different experiment, as I showed you, right? We are now probing the anisotropy, effective anisotropy. I just want you to pay attention to this panel right here, right? I mean, if you look at the magnetization curves, you don't see any difference between the three, as you might expect, right? YIG is magnetic, and you're looking at magnetization. However, when you look at transfer susceptibility, you can clearly see that the two peak structures, I mean the two peak on one side, right? Two peak structures which we associated with the low field and the high field peak that we associated with the surface and the bulk anisotropy, or the interface and the bulk anisotropy, that kind of reduces, and in YIG C60 it goes down in field, implying that there is a reduction in the effective surface anisotropy with the introduction of C60. So one can actually do some DFT modeling. So we've been working closely with Professor Woods, who is also co-author on our recent paper and her postdoc, and they put C60 in between, and indeed they see an increase in the spin density of states. This is important. If you increase the spin density of states, you're again favoring the pure spin transport without any loss, any scattering, and essentially improving the spin Seebeck effect. So it seems to be consistent and also can be effectively understood in terms of DFT calculations of the interface, in anisotropy or the interface magnetism. Okay, I'm pretty much close to the end of my talk. I just wanted to show you a couple of more recent things and ideas that we are investigating here. We actually started looking at stacks of magnetite, Fe3O4. These samples were grown actually from India. They're grown in Bangalore, IISc Bangalore, PLD by Dr. Bhatt and Professor Anil Kumar in his lab. So very high quality. We're getting really good samples. So we looked at a single layer and a triple layer. And the reason we looked at it is because magnetite, copper, magnetite, and there are groups, especially from Professor Ibarra's group, who first reported in Spain, and other groups have also been looking at it, is that as you increase the heterostructure layers, multi-layers, you can actually increase the SSE. It almost as if it scales with the number of interfaces. And remember, the copper is very good as a non-magnetic metallic buffer layer, separating these magnetite films. Okay, so we wanted to sort of reproduce and see if we can see the effect in just three layers, consistent with that. And again, this is one of the papers reported by Ibarra's group, and a combination. Saito is also in there. This is large group that basically looked at unconventional scaling, and especially the increase of enhancement of spin Seebeck effect in multi-layers. So yes, we are consistent. For example, I'll show you our data. This is our spin Seebeck effect. I've already talked about the experiments, measurements. So we see that for the one layer, you hardly see anything. And of course, for the two layers, which is the red, and three layers, you can see that there's a definite increase as the interfaces, the number of layers increases, consistent with what they are also reporting. So we are able to independently look at the temperature dependence. There's a drop in the spin Seebeck effect below 125 volts, 125 Kelvin, and that, as you may recall, is an important temperature in magnetite. That's where the Vervet transition takes place. So basically, we believe that at high temperature, the Seebeck effect is not just Seebeck effect. You also have, it's basically dominated by the anomalous Nernst effect, right, which happens in metallic samples. And below the insulating temperature, you just have, that's why it drops basically. You don't have the A&E contribution, and you only manage to measure the spin Seebeck effect because it goes insulating across. By the way, the Verwey transition is a celebrated transition, metal insulated transition that's well known. It's one of the largest metal insulated transitions in materials. Okay. Recently, we've also been looking at thulium iron garnet films. Why go away from YIG? YIG is very good. Well, we want to play with the anisotropy. Since we know that anisotropy has a big effect on the spin Seebeck, signal, the idea is to see how best we can do that. So turns out that thulium iron garnet is even more sensitive to the substrate, for example. And you can actually induce strain in the film. You can change the anisotropy. And so we started looking at the thulium iron garnet on various substrates. And this is, I think, scandium doped gadolinium GGG substrate. We looked at two different thicknesses, 75 nanometers and 10 nanometers thickness. And basically, we can get very good signal, for the 75 nanometers, for the 10 nanometer, and this is just for 75 nanometers, two different temperatures. Similarly, we did for 10 nanometers, much noisy, as you can expect. So since 75 nanometer film of thulium iron garnet, you have more magnons generated, so that gives rise to a better signal to noise ratio. For the thinner films, it's much noisier. We would also looked at the temperature dependence. We see the same kind of an effect here, a peak here, but the 10 nanometer film did not show any proper trend. So basically, it's too thin for these kind of measurements, but we do see a nice trend here. We also did the transfer. I'm going through this fast. I'm going to get to the conclusion in just a couple of minutes. We also confirmed what Professor Albrecht's group, Manfred Albrecht at Augsburg, they grew these films, and they did some of the work, and they showed that there is basically in plane and out of plane, in plane anisotropy with an out of plane easy axis, giving you a very strong perpendicular magnetic anisotropy in these films, component to these films, and we were able to confirm that with transverse susceptibility also. So again, with a different experiment, we were able to probe the anisotropy and changes in the thulium iron garnet films. It's ongoing work. Something that my new postdoc and student, Amit and Noah, are going to work on is this exciting possibility of gate voltage controlled spin Seebeck effect. I would like to thank Amit for helping prepare the slide here. There's some work reported by Chieling Chin's group. So what they did was, it's like a cross now. Instead of a Hall bar, where you do the longitudinal susceptibility, you have a cross and you actually apply a voltage, a gate voltage between the top and the bottom, right? And essentially, the idea is that you can control the anisotropy by applying a voltage, right? Voltage control magnetic anisotropy is reasonably well known, so you can control the anisotropy. And they showed that these are pretty large voltages. There's a significant difference in the inverse spin Hall signal voltage between no electric field or no voltage and high voltage. So we are trying to do this with our current samples that we have right now. Again, this is for YIG. This is their sample, and so here's some of the preliminary results that already Amit is able to produce in our lab. This is our geometry here, and there is some evidence. It's still needs to be looked at carefully, that with a small gate, even with a small gate voltage of 20 volts, you can see a reproducible change in the spin Seebeck. So he's looking into it, and we are pretty excited. This is for our thulium iron garnet film because it's much better than the YIG. So we expect at a much higher. Remember that the previous study was in YIG by Chieling Chen's group, and they applied very large voltages. So we are excited that possibly this getting this device is going to give you even higher change in increase in LSSE, okay, or change in LSSE rather, field dependence. So basically, this is what we are one of our more recent work. So why do we want to do this? Well, we have already established the role of C60 playing a very important role as far as interface transport, spin transport is concerned. We want to try other things. And in fact, we've just established some collaboration with Professor Kamalakar at Uppsala University in Sweden, who's an expert in growing graphene, hexagonal boron nitride, and other 2D materials on magnetic insulators. So we're going to work with him and his systems, and we're going to do this combination of, transfer susceptibility, anisotropy measurements along with the spin Seebeck to carefully and systematically investigate the role of interface anisotropy in many of these samples, and possibly even introduce topological systems, right? As I showed you, topological Hall effect is interesting, and topological spin Seebeck effect is something that could be potentially very useful and interesting if we replace this buffer layer with graphene, for example, or a 2D, the materials that are really topical these days, 2D materials, 2D magnetic material, 2D ferromagnets. So we can actually look at all these possibilities. And this is just the tip of the iceberg. We're hoping to get very systematic results and to learn more about these interfaces. Just a plug for my journal, please do submit your papers. We have a reasonably good impact factor, as you can see. And we certainly look at a large number of categories here in terms of material science and solid state condensed matter physics. Just to show you some things that we have, some toys, some people here you can see working sputtering system. We have a Dynacool PPMS that is always cold. We have another PPMS that we can play with in the lab where we can do user experiments. We can build our own experiments. We've got facilities for growing films, growing nanoparticles, and all that. And with this, let me thank you for your attention. I apologize for going a few minutes more than the allotted time, but I hope that I've been able to give you a well-rounded picture, an introduction, as well as some insights into the excitement of investigating what magnetic anisotropy is and how it can be used, how it can be tuned to control spin transport and whether it's thermally driven or for any kind of spintronic device, essentially. And I focused on the spin Seebeck effect, which is again something of interest. So thank you very much. As you can see, there's a pre-COVID and post-COVID picture. So now our experiments are all done with masks, and students take precautions and they don't stay close together. So we're following all the guidelines from CDC to make sure that we're working in a healthy and safe environment. Thank you very much. Thank you for your attention.
Okay, thank you so much, Hari, for this excellent overview of various things. And I really appreciate that you have given a very good, very comprehensive introduction to the Spintronics various effects. I'm pretty sure everybody has joined, so I'm clapping on behalf of everybody.
Thank you.
My co-convener, Dr. Braj Singh, someone is not around, but you will see it the recording. Okay, so we have a couple of questions. So we start with Dr. Satya Prakash Pati. Satya, if you are able to ask yourself, please go ahead. Otherwise, I can read your questions. You have several questions, so I leave it to you. Maybe he has some issues with microphone. So first question in slide number 11. He's asking how to differentiate magnon temperature and electron temperature.
Okay, that is just a theoretical, simplified theoretical concept. Okay, it's just a term that people use, theorists use, especially when invoking the Magnon model. There are several models. One of them is the Magnon. One of them is the Magnon phonon model. So these are just temperatures that you get from the calculations, in terms of factored with respect to the Fermi level and the phonon, basically the Magnon system and the electron system. Okay, so it's an idealized equation here. It's a very simple idealized equation. So the more important thing is to show that the spin current is actually indeed depends on this so-called interfacial coefficient. That's the more important message there.
Okay, his next question is, what about role of impurity in temperature anomaly in slide 14? That's
an excellent question. It seems that the role of impurities is not leading to that effect simply because it's been reported by many groups and on many systems in thin films and in single crystal, right? I mean, we're talking about completely different dimensionalities. So it is there, it is robust in many different systems. So yeah, impurities can definitely play a role anywhere. For example, any impurities at the interface is going to, have an effect, have an influence on the current itself, on the spin current itself. However, what you're measuring is basically an average property. So there's always going to be some variation in the data, but the effect itself is there. So it's not something that is ascribed to impurities because the impurity levels are different in different samples that are made by different methods. Some are made by PLD. Single crystal, of course, is grown very in a very pure manner. So that alone cannot explain this anomaly, which seems to be more robust.
Okay, he has another question. What is the frequency of the RF field used in page or slides 19 and 20?
What is the frequency of?
If you recall that.
This one. Our circuit can be, the frequency can be tuned depending on the coil dimensions. We have different coils. Typically, it's in the range of 10 to 25 megahertz. Usually, it's around 12 to 14 megahertz is what we use.
Okay.
For the resonant oscillator.
All right. Mahi, before I go to you, I see Satya has another question, so we just finish his questions. Why in slide 35, why the 10 nanometer film has opposite spin Seebeck effect signal compared to thicker film?
Yeah. Again, I won't trust this because we got a very, our signal was very noisy. And so we really couldn't see, a trend here that we can really call it a trend. I just plotted it because the change is also very small. You can see orders of magnitude, smaller signal. So we don't quite understand because we have to measure more thicknesses between 10 and 75. We do have some samples, but we don't know if this trend is something intrinsic or is just, because the signal is too small. We're not able to make a very clear picture of what's going on here. One thing that comes to mind is that TMIG is extremely sensitive to the substrate strain, right? Even with GGG being the substrate. So 10 nanometer TMIG is going to be completely different from 75 nanometer TMIG in terms of the magnetic anisotropy. So this could be completely different from that, and that may be related, but we don't have a very clear view. We're still trying to do the transverse susceptibility measurements, but we hardly get a signal with this. So we're not able to get a very clear picture of what's going on here.
Okay. Mahi, you please go ahead. Your question.
Well, I was thinking about the maximum at low temperature in the EEG, the spin Seebeck signal, whether it depends upon the impurity, the magnetic impurities.
That's yeah. I mean, like I said, different samples. There's a thickness trend here. This is from one group. Another group here. The peak is not very high and it's kind of broad. So yes, it is certainly, but it depends on magnon scattering, and of course, when you have magnetic impurities, that is going to affect the scattering, right? And that is definitely going to play a role.
So comparing values from different groups going to be a problem unless we really know the proper thickness.
Absolutely. You need to scale it out. You need to scale the thickness out. So what we are trying to do is we are trying to give the best samples with the lowest FMR line width so that it is not compromised by too many impurities. So one way, which is important, as Mahi pointed out, is the impurities in the sample. Is people work with less pure samples, they're going to have a different. They may see the trend, but they're going to have different quantitative values. And so one has to really work with pure samples. And what we try to do when we work with thin films is we get it from one of the best groups that make these films, Mingjong Wu in Colorado State. He's from the Carl Patton's school where they worked on YIG for many, many years. And the FMR line width they give are very impressive. So which means it's high quality films. But you're absolutely right.
Okay, another question. Maybe I didn't listen properly. So did the people try with the carbon IG stuff? Of course, you tried with the C60. How about just with the amorphous carbon or HOPG?
That's a good question. We want to try to try with graphene next, but certainly these things are something that can be looked at. The criterion, I believe, is that they should be semiconducting, and also they should also have a long spin diffusion length. So if there's data available on the spin diffusion length in any of these, that'll be really helpful.
Okay, thanks.
Yeah, thanks, Mike. There is a question from Manoj Talluri. Please elaborate difference between pure spin currents and Magnon spin current.
No, there's no difference. Magnon spin current is probably the purest spin current because it's only spins. The spin angular momentum is getting transferred without actually the charge moving, right? So that's the pure spin current because there's no charge moving. So you're separated the charge because it's an insulator. And the spin angular momentum is transferred because you apply a magnetic field. So you have the precession of the spins, and that's the one that gets transferred, as I showed in the cartoon. Right? Let me go back. This little cartoon here shows you roughly, what we mean by this so-called wave magnon that getting transferred. So it is a type of spin current. It's probably the purest, form of spin current, in the sense that there's no external entities like charges moving.
Yeah, good. I have one or two questions, then we can wrap up. In the C60 case, I forgot the slide numbers, but I'm sure you can find it. The IG C60 Platinum. So there was a thickness dependence of the ISHE signal of the voltage, and there was a peak.
I'm getting to that.
Yeah.
This one?
No, you please continue.
Yeah.
So on the right side, you see for C60 thickness about, 5 nanometer, you get a peak. What is the reason for that? Because C60, the spin diffusion length is much, much larger.
Yeah. The short answer is we don't really know, except that it seems to correlate with the FMR pumping experiment from a different group. So they also see the same thing, that at this 5 nanometers, there seems to be the highest enhancement and if you look at this, really, we don't see any difference between 140 and, it's just, so at this point in time, we don't know the precise answer for that particular, we just know that 5 nanometer C60 certainly improves the LSSC and gives you the highest value, but the mechanism itself, one has to look into carefully. I mean, for this, we need to study the interface, both sides, with the platinum and with the YIG, to look at any diffusion that prevents or whatever it is that can. I mean, the other thing is, remember, C60, the bonding between carbon and the d orbitals, that will affect that's what we think from the DFT calculations seem to indicate that plays a role in the reduction of the surface magnetic anisotropy. Now, whether this 5 nanometer thickness favors an increased bonding or not is something I cannot tell you. So we don't know.
Okay, just as a similar note, you know that although C60 is low spin orbit coupling material, but when you deposit, then there is something called the distortion enhanced spin orbit coupling. So there are reports, and even we are just finishing our experiments on C60 cobalt iron boron.
Mm-hmm.
We found significant amount of spin pumping at the interface.
Mm-hmm.
So C60 is actually playing like a high spin orbit coupling material, which is not. But it is just because it is deposited and it is this curvature enhanced spin orbit coupling. So in terms of the spin Seebeck effect, do you think the C60 is not only just acting as a barrier for this good interface, but also contributing, so to say, to the spin Seebeck effect?
That's an excellent question. Again, as I said, the mechanism is at this point, we don't really know what is leading it. Right now we're just looking at the general aspects that of the C60 on top. But as you pointed out, C60 itself is interesting and can have a dramatic effect. Now, whether it enhances the spin-Seebeck effect, what we should try to do is look at probably C60 on different materials, for example, not just YIG, because in YIG you have the surface anisotropy, whereas you don't have that in magnetite, for example. So we haven't done that yet, C60 on magnetite. But if we go to other ferrites, for example, spinel ferrites, and do the same experiment, we'll be able to see what the role of C60 is with and without C60 on these other materials. So yeah, it's a very good question. And in fact, I would like to talk to you more about what you're observing with your interfaces, maybe offline at some point.
Yeah, we can discuss that later on. Last question from me, before there is one more question from a participant. If you take the C60 with a normal metal, you know, this interface comes into picture because of the hybridization, and the C60 at the surface of the interface becomes indeed magnetic. It has its own magnetic property. It can contribute
there's a child that has more questions. I'm not able to hear properly.
Yeah, I don't know. So somebody else has gone.
That's fine. That's fine. It was nice to get some interruption.
Yes. So in terms of E, because it's an insulator, do you think there is also a spin interface happening where C60 is getting magnetic?
Yes, that's a possibility. And in fact, this is very important because it opens a whole new can of worms. Not a can of worms, but a can of interesting things. Basically, you're talking about proximity-induced magnetic phenomena. And there's a lot of interesting work that's going on. In fact, the whole 2D ferromagnetism community is excited about that particular interface, magnetism. So there are many examples where, especially in 2D materials, where the material itself doesn't show a very high ferromagnetic response, but when it's interfaced with some other non-magnetic material, it shows enhanced response. And so some of those things could be playing a role too. Again, we have to do more experiments and more careful experiments to understand the proximity-induced ferromagnetic aspects. And yeah, you very rightly pointed out that could play a role. Yes.
And the paper just accepted, or it's already published, this material origin? Because I'm really curious to read that paper.
It's already published. It came out in, I think, February, March timeframe.
Okay, then I will read it. Okay, Abhiru, could you ask your question? Probably this is the last one.
Yeah, am I audible? Hello?
Yes, I can hear you.
Yeah, I just curious about the fact that this 5 nanometer thickness, what is the diameter of this cobalt 60 molecule? Is there any integer link with that 5 nanometer?
I don't think that's, the C60 itself is quite small compared to the thickness. It's not a monolayer.
Okay.
But yeah, but I do need to refer to the expert who deposited this. I can certainly check with Professor Nguyen because he's the expert on C60, and he uses some kind of a modified CVD technique to really make very, very good interfaces.
Maybe I can just to comment on that. So C60, the monolayer thickness is about 1.4 nanometer.
Yeah, so it's a few monolayers. Yeah.
Yeah, so it's few monolayers. So it's not just a monolayer. Okay. Yeah, please continue.
Or to complete C60 layers there instead of any the periodicity would be completed. So is there any such role in the spin conductance, or it enhance the spin mixing conductance?
Again, it is hard to see. We have to have some kind of a microscopic model that actually models the spin mixing conductance, taking into account the density of states and all those things for C60. The general model right now that I showed you, that's just a toy model. Just puts that just scales the thickness with the that's what it is. But a more comprehensive analytical model is what is needed. And for this, some people who are experts in DFT should get more involved in this and try to see by increasing the, as you pointed out, by increasing to layer by layer, 1 monolayer, 2 monolayers, 3 monolayers, what happens? So that is needed.
Okay.
But because we are growing C60, so deposition of C60 at such a high precision is very, very challenging. It's a very much volatile material, and mostly you deposit this thermal evaporation. So the rate is not really that controllable like in sputtering or MBE. Okay, so it's like highly challenging to say, okay, I want half monolayer of C60 monolayer like that.
Yeah.
So you can only probe that by DFT, where they can actually change the number of atoms and they can see until how much it is effect, kind of having an effect. Okay.
Yeah.
Okay.
So we are planning to do this experiment with graphene. So wait for the results, and we'll have a better idea of what's going on there.
Graphene is a little bit more straightforward, I would say. All right. So I think it's time to call it a day. So
thank you
so much, Hari, for this wonderful lecture, and thank you so much, everybody. We had roughly 50 participants, and that's really great. And I hope to see you next week, same time, same day, and we continue till end of the year. And I don't know if I have plans to continue after January or not, but at the moment, speakers are fixed till Christmas time. So with this short note, thank you so much again, Srikanth.
Thank you, everybody, and namaskar, and hope to enjoy some more talks, in your Spintronics series.
All right. Please stay safe, stay healthy. Good night. Bye bye.
Bye bye. Good night to you all.
Bye.
Bye.